Okay, thank you very much, Adrian. Good afternoon, everyone. Thanks for giving me the chance to present a bit of our work, which is very much appreciated. And well, to give a little bit of context, I want to start with a short story about deceiving tourists in Ecuador. So I could see, okay. There is a sculpture park near Quito where the line of the equator is painted on the ground. And curiously, there is a basin that you can see, if you can see my pointer is over here, is a basin with water in it and right on the equator line. So as tourists approach to this basin, a person announces that he will make a small demonstration. So he throws some leaves on the basin and then pulls a plug from underneath. And the water drains without spinning, as evidenced by the non-spinning of the leaves. Then the person takes the basin a few meters to one side of the equator line, pours water into the basin, throws some leaves at it while pulling the plug. Again, the water spins clearly one way as it drains. Then he takes the basin to the other side of the equator line and repeats the experiment. This time, the water spins the other way. He then gives some explanation involving the Coriolis force and blah, 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 and people applaud. And well, this unfortunately is just a trick. In reality, the Coriolis forces in the basin are too small compared to the inertial forces as represented by the Rossby number, which we have here. And well, it does work for large systems, but not for small things like water in the basin. Because the Rossby number in a very large circulation system or like a hurricane, the Rossby number is very much smaller because of the sheer size of the system. Well, but additionally, the line painted on the ground does not really mark the actual equator if we think of the plane that is perpendicular to the Earth's rotation axis, like instantaneously. So this plot on the left is marking the location where the rotation axis of the Earth, like instantaneously, intersects the Earth's surface, the actual pole. And it wobbles around with an amplitude of about 18 meters as measured on the ground. And there is also, well, you can see there is a secular trend. This marks just like the center of the spiraling. And this trend is also shown here. This is a highway in Mexico that is labeling the location of the Tropic of Cancer, and it's just following this very big trend that we see here. But there is also a smaller timescale variation over months or weeks that takes place. So the line of the equator is moving constantly. Maybe not during the time of the demonstration, but over weeks and months, the line of the equator is just moving up and down by about 18 meters. So that's the situation with that trick that you see sometimes in Ecuador. But now I want to discuss like how can we measure the Earth's rotation so well? Well, it turns out that we can do it if we have an inertial frame. We need a reference frame, an inertial frame. And the best realization of that we can obtain by looking at the correlation or at the time correlation of very distant radio sources like quasars as observed by different observatories on Earth. If we do this with many quasars around the Earth, we can define what is called the celestial reference frame, or CRF. The instantaneous rotation axis of the Earth is monitored constantly using this reference frame. Okay, now let's go into matter a little bit more. This slide is representing the gravitational torques from the sun and the moon, and they can change the rotation axis of the Earth due to its oblateness of the Earth. So we know very accurately the orbits of the apparent orbits of the sun and the moon. So we know very well the gravitational forces that are acting on Earth. And as I just mentioned, we also know very accurately how the Earth is moving in space. In other words, we know the response to those gravitational torques. So the response depends directly on the Earth's structure, particularly on the moment of inertia. So the situation is conceptually the same. I hope this video shows. The situation is very much the same as when we are cooking and you want to know if an egg is fully cooked or not. So what you do is to spin them. If the egg spins very fast, that means that it responds to our torque with fast rotation. That it means that it's fully cooked, it's completely solid. And if it doesn't, then it is fluid inside. It's exactly the same technique. Now let's look at the changes in the Earth's rotation. Now we have here the nutation, which are changes in the orientation of the Earth's axis. This is not taking into account the secular change, which is due to precession. This is just like the faster motion that are more or less like interannual or longer, but not as long as the precession. And we also have that the rotation axis, or the rotation of the Earth, is not only the orientation, but also the rotation rate is changing, and it's something that we call the length of day. So it's the period of the rotation of the Earth. And these two need to be, torques from the atmosphere and the oceans affect the direction of the Earth and the length of day variations. And if you take them into account, you still have a residual in the signal that is supposedly coming from the core. So indeed, the atmosphere and oceans can exchange angular momentum with the mantle, and yeah. So after all these residuals have been after all these effects have been taken into account, there is still a signal that can potentially give us information about the core. And well, particularly, we can get some idea about the core-mantle boundary, such as characteristics like topography of the core-mantle boundary, like conductivity of the lowermost part of the mantle, or the presence or not of a stratified layer at the top of the core, the strength of the magnetic field inside the core. All these things affect the way the Earth responds to those external torques. And okay, so let's go back and talk about precession a little bit. So we know that the torques, essentially from the moon, are more important than torques from the sun, are the ones that are causing the precession of the Earth. So in this animation, I'm going to show what happens to the core when the Earth precesses, because the orientation of as you know, in precession, the orientation is just changing over a period of about 26,000 years. And the core, being fluid, well, cannot follow instantaneously the motion of the mantle. So it lags a little bit. That means that the fluid core as a whole object has a rotation axis that is slightly different from the rotation of the mantle, from the axis of the mantle. So in this animation, you're going to see that the core is spinning at a different axis than the mantle. And we're going to see this from the space frame, like an inertial frame, and then we switch gradually into the mantle reference frame, and then we see what happens. So this is about we go in, and then we slowly switch into the mantle frame. So the mantle was going to stop moving, and you will see what the core appears to be doing as we undergo precession. So it's basically a motion of the core where the regions near the poles are going like in a circular fashion, and the regions near the equator are going just up and down, north and south. And curiously, this flow, this differential motion of the core and the mantle, is by far the largest flow that takes place in the Earth's core, more than the thermal and the compositional convection that might take place as well in the core. Okay, so let's keep going with the rotational eigenmodes. So the core moves almost as if it was a rigid body in rotation. This is an approximation that geodesists use very often. So with that approximation, we can show that the Earth has 4 rotational eigenmodes. The one I want to focus for a moment is the free core rotation here in red, which is very similar to the flow associated with precession, the one that I just showed, given that the spin axis of the core and mantle are slightly misaligned. The period in inertial pace is much shorter for the FCN. It's about 431 days compared to the 26,000 years of precession. And also the amplitude is much smaller. The free core rotation, or FCN, can be excited if there is a forcing with sufficiently close frequency. There is in fact such a forcing. The component psi1 of the the tidal component of the lunisolar forces. There is specifically one component that's called psi1 that has a period of about a year and is the closest in period to the FCN, which has a period of 300. Well, the forcing has a period of 365 days, while the FCN has a period of 431 days. So that's the closest. And so there is the possibility then that the FCN becomes amplified resonantly because of the forcing of this tidal force. And if you measure the lag, the time lag, the phase lag between the forcing and the response of the Earth, then you can have an estimation of the quality factor of that resonant mode. And it turns out that the quality factor is about 20,000. And so far, we have not obtained a good explanation of why this quality factor is so high. If we take into account the viscosity of the Earth, that quality factor should have been much larger. And to explain it, then we would need a viscosity that is way too large, like about 4 orders of magnitude larger than the molecular viscosity that we expect to exist in the core, Or the other possibility is that there is a unreasonably large magnetic field at the CMB. So we still don't have a very good idea of what's going on. One possibility that we suggested a while ago was that maybe because of the flow due to precession was so strong that maybe the flow near the core-mantle boundary was very turbulent, and therefore the eddy viscosity, the effective eddy viscosity would be much larger. But there are a couple of papers, one by Bruce and one by one of my students that just finished his dissertation just recently, that actually killed that idea. The flow at the CMB is just barely, it's not really fully turbulent, according to these two calculations. Okay, so I want to keep going and give an overview of some of the Earth's eigenmodes. So we have, as I explained earlier, these rotational eigenmodes, these four, with the time scales as measured in the terrestrial or mantle frame. And these are the FCN, the FICN are diurnal. The Chandler wobble, the inner core wobble are much longer in period. And these particular ones, these three sets of eigenmodes, the torsional oscillations, Mach waves, and the MICG mode that is related to the gravitationally coupled inner core, have very long periods, and they are probably present in the length of day variations as measured from the VLBI data. So the groundbreaking work of Nicolas Gillet and collaborators provided a very good, convincing arguments in identifying the torsional oscillations in the core. They took magnetic data, down continued to the CMB, to the core-mantle boundary, and computed through an inversion what the flow should be to give those magnetic oscillations. Then, under some assumptions, they obtain a flow, and the length of days variation associated with that flow that is shown here in black matches very well the observed length of day variations, which is in red. So that's a very good argument that the length of day variations that we see can be, that are actually originating from the core, and they are the signature of the torsional oscillations. I hope I'm going okay with time. Yeah, I think I should speed up a little bit more. So I can finally arrive to our contribution to the community studying this. So we want to build a numerical model of the Earth's eigenmodes, and particularly those associated with the core. So we want to look specifically at the torsional oscillations or any other eigenmode that might be involved in the length of day variations. We want to include an inner core gravitationally coupled to the mantle and magnetically coupled to the fluid core. So we have not completed all the steps that I'm listing here, but I want to, at least during this presentation, show what we have achieved so far. And one peculiarity is that viscosity that we need is required, because otherwise the problem becomes ill-posed. And this is something that we know from the work of Michel Ritor like 20 years ago. And we also want the possibility of to model a stratified layer at the top of the core, because there is a suggestion from Bruce Buffett that the some subtle flows that are inferred at the top of the core can be caused by magneto-Archimedes Coriolis or MAC waves in the core. So for that, you need a certified layer at the top of the core. And we can do that in our code. We use the Businesque approximation. And with that, we can see if we can find those MAC modes as Bruce Buffett suggested a long time ago. This is actually work ongoing by one of our students at the observatory, by Fleur Severin. I should have mentioned here. But I'm not going to show the results from that. It's pretty much very advanced state. But I'm going to focus more on this part, on the torques that are exerted by the fluid on the mantle. And these are electromagnetically originated through by currents that flow in a very thin conductive layer at the bottom of the mantle. So this layer is hypothetical. It's also something that has been under discussion for a long time. We don't really know if it's there or not, but a good indication that it could be there is that the LOD variations, as demonstrated by Nicolas Gillet, match the LOD observations very well. So that's a good observation, a good indication that this thin layer at the bottom of the mantle might exist. So we have a parameter called C prime that is basically the conductance ratio between the mantle and the core. And if you assume that the conductivities of both are the same, then simply this ratio will be simply the height, the width of this conductive layer at the bottom of the mantle. So this we can do easily in the code in our numerical approach. It's not very difficult, given that you can actually do this as a boundary condition without the need to solve for the induction equation in the layer itself. Okay, so I'm going to keep going, and some of the parameters that we use are actually dimensionless parameters that are related to different timescales that appear in the problem. So we have the rotation, viscous, magnetic diffusion, and the Alfvén wave timescales. These are 4, and the ratios, different ratios of these, give place to the different dimensionless numbers, like the Ekman number. And in parentheses here, you see the value of that parameter as we believe is in the actual Earth. So the Ekman number is one of the smallest parameters. Is really very small. There is the magnetic Ekman number, the Leonard number that is related to the strength of the magnetic field, and the Lundquist number that also relates to the magnetic diffusion. Okay, and so for our model, we're basically going to solve these 3 equations. The Navier-Stokes equation for the motion of the fluid, the induction equation for the magnetic field, this in the outer core, in the fluid core, and in the inner core, which we take as conductive, electrically conductive, then we simply solve the magnetic diffusion equation. In the future, we're going to put as well the angular momentum balance between the mantle and the inner core. But so far, we haven't gotten to that stage yet. And we have our boundary conditions, continuity of the magnetic field and the electric field. And we take a background magnetic field static that is going to represent the geodynamic. And well, with the risk of boring you a little bit, we follow the following numerical method. We use a like sort of standard poloidal toroidal decomposition with a spherical harmonic expansion. And the only thing that probably is not familiar for everyone is that we are going to use Gegenbauer polynomials instead of Chebyshev polynomials. Well, Chebyshev polynomials are a special class of Gegenbauer polynomials, but these ones have the advantage that the derivatives of them can be represented by discrete matrices, which give us a little bit of a numerical advantage over the regular Chebyshev methods. So we basically write, well, we assume that all quantities, all dynamical quantities are oscillating in some harmonic motion. And with all these other expansions in place, we end up with a generalized eigenvalue problem. And lambda, the eigenvalue, is going to have the real part representing the damping, and the imaginary part will be the oscillation frequency. This is all what our code does. So I'm going to explain a little bit the background magnetic field that we use. We use essentially a poloidal magnetic field that it can be either dipolar or quadrupolar in this that has this shape. This radial function, we are following what Luo and Jackson in 2022 used, which is very convenient. This is represented here. And we take the amplitude of this function so that the RMS radial cylindrical magnetic field is about 3 milliteslas, which is what Nicolas Gillet expects from his calculations. So that leads to a Leonard number of about 10 to the minus 4. We have again our conductance ratio that I showed before. And just for comparison, Nicolas Gillet uses another parameter for the conductance, for the different conductance of the mantle, and is written like this, which is related to our C prime through this relationship here. Okay, so the results. First, we're going to do the comparison with what Luo and Jackson did, which is actually a very great help to have that paper, these results, because they help our validation immensely. And here I'm going to show the results in a this is essentially the complex plane and showing the eigenvalues in the complex plane. So sigma is the real part, and omega is the frequency. And this is in the Alfvén time units. So this is about, this is actually very low frequency. I would say that this is about 6 years in period, this line over here. And we see 3 different, well, first of all, the comparison between the two is very good. So this is the results from Luo and Jackson, and this is our code. And we see, we see 3 different sets of modes. These are what we call magnetocoriolis modes. These are torsional Alfvén modes. And this other bunch over here are inertial modes. So we are going to focus especially on these torsional Alfvén modes. Now, we are going to include viscosity. So in this case that I showed you, this is an inviscid, as I hope you can see the parameters here. There is no viscosity, that means that the Ekman number is 0. There is no inner core, the mantle is insulating, and there is a dipolar background magnetic field. And those are the conditions for the study, for the comparison. But now we're going to include viscosity. So what happens? In the color indicates here the Ekman number. Here is like a logarithmic scale, and the green is more viscous and red is less viscous, approaching, well, the smallest number that we can achieve. 10 to the minus 10 almost. Oh, sorry. And we see that in this plot, if the Alfvén number is too large, then the torsional oscillations do not really exist as a different set. They are actually intermingled with the magneto-Coriolis modes over here, but they only show up when the viscosity is low enough. And we can see a little bit of the little dance that, or the path, the crazy trajectory that the torsional oscillation modes follow as the viscosity is decreased. So there is a lot of interaction between modes eventually until they come out from the group of the MC modes. This happens. This is what I'm marking here, the line of the magnetic Prandtl number. There is about 1 here. The magnetic Prandtl number I didn't mention is the ratio between the kinetic diffusion or viscosity really compared to the magnetic diffusion. So it's about, for the Earth, the magnetic Prandtl number is about 10 to the minus 6, which is very small. Okay. Now I want to show you the, if my time is okay, I want to go quickly over this. Now we are going to change the conductivity of the mantle. We're going to change the ratio of the conductances as this axis is shown here. And we're going to also change the Leonard number. This is just because we're trying to follow or compare with the 1D theory that exists about torsional oscillations that predicts that around Q equals 1, the modes are completely damped, and that they only manage to have that they are not so damped when Q is much smaller than 1. And so we try to compare with that. So color represents the presence of torsional oscillations, which is actually in color here, for a different number of runs that we made with the code. And what you see that is really the agreement is only kind of marginal, because there are situations in which the Q is definitely well, even 1 or larger, and we still have torsional oscillations that are not fully damped. So the agreement is marginal at best. Okay, I want to show, well, this same plot, but I'm gonna go over one of these ramps that we made, changing the conductance ratio, because you'll see something interesting. The frequency changes, the damping increases as you increase the conductance of the mantle. The toroidal to poloidal energy of the mode changes as well. The dissipation ratio between ohmic and viscous also changes, increases. The main characteristic quality of the torsional oscillations, meaning the kinetic to magnetic energy ratio, which should be close to 1, is about the same, because they're very good present. And the torque on the mantle increases linearly with C prime, with the conductance ratio, which is well, something easy to see here. I should explain here that this torque in Newton meters is not a dimensionless number that I put here, because I gave an amplitude, a specific amplitude to the mode to match what Nicolas Gillet suggests is the RMS azimuthal velocity of the flow from his dispersions, which is about, it's a number of about 300 meters per year. It's a very slow, it's about 10 to the minus 5 meters per second. So if I give my eigenmode, which is in principle an arbitrary amplitude, if I give the eigenmode this amplitude, then I can compute the full dimensional torque for the mantle. And we are hoping to get to 10 to the 17 or larger, because that's the number, that's the torque that is required to cause the length of day variations that we observe. It's a number between 10 to the 17 to 10 to the 18 Newton meters. So we see here that we don't actually make it, but it's very close. And if we change the Leonard number, the torque increases, and all the other quantities also change as well. Particularly, there is a dip in the, or a peak in the damping. And there is a dip in the toroidal to poloidal ratio. The frequency changes, and so on. And what happens if I keep increasing the Leonard number? Then this peak is more pronounced, and there is a very clear change in the frequency. There is a huge dip in the toroidal to poloidal ratio, which this means in particular that the quasi-geostrophy character of the modes is somewhat lost at this point. And also, well, we cannot really call them, well, this change is not so big, but in other cases that we have seen, this ratio goes very far from 1, which makes us, we wouldn't really call them torsional oscillations if this ratio is not close to 1. So I keep increasing the Leonard number, and we see, well, similar behavior, some very weird things. The torque eventually plateaus to a very high number. This number here is actually what we need for the LOD variations. And I want to zoom in a little bit into this region here to see what's going on. And you see a number of things. The frequency changes, but there is a strange behavior here. And you actually realize that it's an avoided crossing of a magnetocoriolis mode with the torsional oscillation. So it turns out that there is a magnetocoriolis mode that kind of goes, like appears from the background and takes the place of the torsional oscillation here. The torsional oscillation is kind of lost, but then is replaced by this other one. And then this happens again. So it's like a successive exchange of identities as these avoided crossings take place. And well, okay, since I don't want to take up a lot of time, this is the last case, a larger Leonard number, and we see that this torsional oscillation mode actually splits into two. Two new modes appear, and there is again the peak in the damping. The torque is also quite substantial, and so on. And the last one here is what happens when you keep the conductance ratio fixed and you simply change the Leonard number. And the Leonard number leads to a change in the torque that is about, this line over here has a slope of about a half. So that means that the torque is proportional to the Leonard number squared. But as you can see here, the dynamics are really intricate. There are lots of magnetocoriolis modes that come in and out and cause these avoided crossings with the torsional oscillation. That eventually they manage to, well, to tear it up completely apart, so that there is no torsional oscillation anymore as you increase the Leonard number. Well, let's see. I'm still okay on time, I suppose. I want to show what happens if you change. Oh, this is changing the. Here I was changing the mantle conductivity. This is also changing the mantle conductivity, but I'm fixing my attention to the torques. And well, let me go to this slide instead to have an overview of the torques. This is the torque on the mantle from a set of torsional oscillations. And again, as I explained, I give this amplitude to the mode to match what Nicolas Gillet suggests, and so that I can compute a dimensional torque to compare with what we need, the target torque that we need for the length of the variations. So this continuous line corresponds to a magnetic Ekman number of 10 to the minus 8, and the dashed lines to 10 to the minus 7. And you see that, well, the Earth is 10 to the minus 9, but I cannot go to 10 to the minus 9 in magnetic Ekman because of then I will be very close to this Ekman number, 10 to the minus 10, which would in turn mean that my magnetic Prandtl number would be too close to 1. And we don't want that because then the torsional oscillations do not behave, do not exist. So we cannot really go too close to 10 to the minus 8. And this is about the smallest Ekman number that we can get. So we cannot really go smaller than this. But in the end, we know that the torques scale in this way, and the torque on the mantle scale on this way, in this way, according to, well, it depends on what mode you look at, because the different modes might have a different constant of proportionality here. But this is a nice result. I'm not sure if this has been shown before. I haven't really looked, but it might be a very simple result. Okay, maybe for the sake of completeness, I want to show what happens when you change the inner core conductivity, because this is the most drastic change that takes place. As you put an inner core and you start increasing the conductivity from insulating to fully conducting, a few changes take place. Particularly, like these modes, these torsional oscillations disappear, and they are affected. I mean, sorry. This one, for example, is changes in frequency. This one disappears completely. This one also disappears. This one changes in frequency. And you can see that the magnetic to kinetic energy ratio, how it behaves when you do that. We expect that it should be 1, if you can call it a torsional oscillation. And then you see that it goes up. So it means that these modes become magneto-Coriolis modes as you start increasing the conductivity of the inner core. This is what happens to the damping, and this is what happens to the toroidal to poloidal energy ratio. This is a very simple way to characterize the columnarity of the nodes, because as long as they are very columnar, then the toroidal component must be much larger than the poloidal one. But you see that the modes lose the quasi-geostrophy character, the columnarity character, as you start increasing the conductivity. And this is how the modes look like. I'm showing here with a star the modes, and this is how the velocity, the azimuthal velocity looks like. This is how the azimuthal magnetic field looks like. And this is for an insulating core, which I put like a wooded texture to remind that this is an insulating. And this is what happens when the core is conducting. So you see very interesting changes. Note that the intensity of the flow is pushed away from the inner core, and there is an intense area, a patch of magnetic field near the inner core boundary. Now I'm going to show you a little bit more of this. This is a comparison between no inner core, insulating inner core, and conducting inner core. These two cases, the no inner core and insulating inner core, are very similar. Actually, the presence of an insulating inner core does not really change things much, but the presence of a conductive inner core is really important. This is how the modes look like. This is the star, showing what mode I'm talking about. This is let me go back. This is insulating. The line overlaps. It should be, the green is just under the blue. But this is the insulating part, and this is this is the conducting one. So you see that the modes are very different. This is the second harmonic, and again, the same situation happens. The mode is pushed away from the inner core, away from the tangent cylinder, and there is an intense patch of magnetic field near the inner core. Okay, so with that, I want to conclude. So we have a marginal agreement with the one-dimensional theory, which is, well, not surprising because our model is completely spherical. And there is a continuous metamorphosis of the modes from torsional oscillations into magnetocoriolis, given when you change a few of the parameters, particularly the conductivity of the bottom of the mantle. The electromagnetic torques, which I didn't explain it, but the electromagnetic torques on the mantle are substantial, and they can lead to angular displacements of about 0.1 degrees, which I think is consistent with observations. The inner core torque is only weakly dependent on the mantle conductivity, which is not surprising, but the inner core seems to push away the modes away from the rotation axis when the conductivity is changed, as I try to remind here. And with that, I conclude. Oh, sorry, that was too fast. Thank you.